Recording is on.
That took a while. Okay. Let's see. Okay, I want my head to show, so. Okay, there we go. I think it's working. Let me know if you can't see my screen. Feel free to type something in chat, make sure it's working. If you haven't already, the cool thing about this Jitsi thing is you can also make polls. So yeah, yes. I just made a random poll, but it's next to chat. Okay, so we'll get started. Let's see. Okay, so yeah, I think you can double click my screen to make it larger, probably, since I'm sharing. Yeah, that's fine. Okay, so we're just gonna do some complex numbers and geometry problems. So first, let's just review, what complex numbers do when you multiply two complex numbers in the complex plane. So the main theorem is just if you have like W and you multiply it by R cis theta, then the magnitude will get multiplied by, so let's say this is Z, then Z will have magnitude like this times this. And the argument of Z will be just like the argument of W plus theta. Oh, let me admit one more person. So, just as a reminder, if you have a complex number, this is the magnitude. Like, this is the magnitude. It's like if it's A plus BI, then the magnitude is A squared plus B squared, square rooted, I guess. So it's the distance from the number to 0 plus 0i. And the argument is just the angle it makes with the positive real axis. So that's the argument of Z. So whenever we talk about angles, we'll always go from the positive real axis, counterclockwise. So, if you multiply a number by like 2 cis theta, then, the magnitude will multiply by 2 and the angle will be, you'll add theta to the angle. So that's what multiplying by 2 cis theta does. So if you start off at 1 plus 0i, your magnitude will double. And if theta is like 60 degrees, then you'll end up at the 60-degree mark. So this will be, 2 cis 0 plus 60. And that's true for any complex number, not just one. So, we can prove this with trigonometry or without trigonometry. Yeah. By the way, can everyone hear me okay? Okay, I see a yes in chat, so that's good. Okay, great. So, let's just prove this without trigonometry because I usually do it with trig. So, if you have a complex number x plus yi, so we're going to do two things. So one is, if you multiply by I, that rotates by 90 degrees counterclockwise. So, if this is your original number Z, you'll end up right here. So let's see, why this is true. So, you have x plus yi. I multiply by I on either side, be xi, and then, plus yi squared, which is minus y. So that will be negative y is the real part, and xi is the imaginary part. So this is like xy. Then negative y will be like right here. And then this will be negative y comma x. So, like this will be x, this will be x, this will be y, this will be y. So, this corresponds to negative y plus ix or xi. So we can kind of see, these are congruent triangles, like this one and this one, they're congruent because, well, it's true by like SAS similar congruency. So that means this is a 90-degree angle because this is a 90-degree angle. So statement 1 is true. If you multiply by I, you'll rotate by 90 degrees, counterclockwise. Statement 2 that we should check is like, if you multiply by like an arbitrary complex number, let's say you multiply by, I'll just say arbitrary. Let's say W. So let's just take W to be like 3 plus 4i. So if I multiply, so here's like, 3 plus 4i. So, you'll have, no, let's make it like 4 plus 3i. So it doesn't matter, but 4 plus 3i. So let's call this angle phi, and this can be 4 plus 3i. So, this will be 4, this will be 3, this is the real, the imaginary and real axes. And what we're going to do is, basically, we need to use the fact. So let's say we start off with an arbitrary complex number z. So that's z. If I multiply, so if I multiply z by 4 plus 3i, that's the same as you take 4 copies of z. So if you multiply by a real scalar, like 4, that's just like z plus z plus z plus z, right? So you just triple it and you keep the angle the same. And then you add 3 copies of I times z. So we said I times z was like this. It's like a 90-degree angle to it. So that's iz. And we add 3 copies of that to 4z. So plus iz plus iz plus iz. So then you can see, this point will just be, let's say, like 4 plus 3i times the complex number z, which we started with. So then, if you look at this triangle, it's a 4 by 3 by 5 triangle. So it's similar to the triangle I drew up here. So this angle is phi, just like this is phi. By the Piparian theorem, the distance, so this will be 5 times the magnitude of z, because each of these units have length like magnitude z, right? So the output is 5 times magnitude z away from the origin. So what we proved is, if I multiply the starting number z, which is right here, by 4 plus 3i, the magnitude got multiplied by 5, and the angle got rotated by phi in the counterclockwise direction. So multiplication by 4 plus 3i, it does what we expect, what we wanted to show it does. Rotates by phi equals like tan inverse of 3/4 counterclockwise, and scales the magnitude by 5. So, you can replace 4 plus 3i by any complex number, and this is always true. So what this means is, if you multiply z times w, you just basically, you multiply their magnitudes and you add their angles. So if Z was like R1 cis theta and W was R2 cis phi, then you just add their angles and you multiply their magnitudes. Yeah. So so that's how you can prove it without trig. Any questions on that? So this will be the main theorem for today. So this is the main theorem. Okay, so I guess we can do some problems with this. Let's see. Okay, so I don't know what we should do first. I guess I'll just pick one. So yeah, sure, we can do this. So the problems will be, I'll just put the problems up. So we'll do that one, and then we'll do these two. And then we have time, we'll do more, but yeah. So we'll need to use the main theorem a bunch of times. So you should be very familiar with the main theorem, because this is used to prove the Mavre's theorem, and it's like the most important complex number fact about complex multiplication and geometry. And it's used like all the time on AMC 12 and AME and such. So yeah, I guess we can look at number one. That's fine. So you have a circle omega. So let's just do one. Output, and it's got radius 1, and you have a pentagon that's regular inscribed in it. And you want to find what is like AB times like the product of the distances from A to the other 4 vertices, right? So this is 1. Let's just make this like what? Let's put it in the complex plane. So this is 1 plus I times 0. And I'm just going to assume some facts about complex numbers. Let's see, would using linear transformations also work for 0? Well, so linear transformations, it's like the same as, the idea is kind of similar to, the theorem we did up here. So, you can do, you can define a linear transformation like cosine theta, or what did I call it? Phi, right? Whoops. So it's like the same idea, and you can kind of prove it with trig, or, negative sine phi, cosine phi. So, this is a rotation matrix. It'll rotate a vector in 2D by phi counterclockwise. And it's kind of like the same idea. So yeah, I don't really see it like as a distinct way, but it's like a different notation. So yeah, that would also work, because you could then left multiply it by if Z had like coordinates R cosine theta and R sine theta, then you can just multiply this matrix. It's a rotation matrix, and if you apply it, I think you'll get like the sine and cosine addition formulas for the output vector. So yeah, I guess that works. Hang on, let me see, is this right? Yeah, I think it's like this. So yeah, I guess that's fine. It's a different way of writing it, but it's kind of like similar to like the trigonometry proof, which we didn't cover, but yeah, that's fine. So if we go back to this problem, yeah, you can also use exponential form and Euler's for that. Yeah, that's true. Yeah, I think you can like prove those things independently of the trig formulas, but I'll have to remember how to do it. Like, there's probably lots of ways to like build up the proofs so that like they don't rely on certain trig facts, or they do. There's probably multiple ways to build up the foundations of the proofs, to use certain theorems or not use certain theorems. But let's just do this problem. So, let's say omega, which is this W thing, I'll call it omega. It's a Greek letter, is a fifth root of unity. That's not 1. So this will be, omega at omega. This will be like omega squared, omega cubed, omega to the 4th. And this will be omega to the 5th, which is 1 right here. So those, some people call it the affix of a complex number. It's just like, like you could say, if you want this point in the complex plane to be A, you just say A is like the affix of that point or something. So I don't know if people use that word anymore, but anyways, this has everything is on the unit circle with magnitude 1, and they're all like 72 degrees apart. So what we want is, is there a question? Yeah, someone, I'm gonna mute everyone just so there's no background noise. Okay, so let's see. Yeah, so basically what we want is like the length of AV. That's gonna be, so in complex numbers, right? If you do like A minus B and you take the magnitude, that's the distance from A to B, right? Because here's A, here's B. A minus B is like that vector or something, or that's B minus A. And then if you put B minus A at the origin, so if this is 0, then this will be B minus A. So this makes a parallelogram. So B minus A is the distance from the endpoint of A and the endpoint of B, if you think of the complex numbers as vectors. So basically, this will be 1 minus omega, and then AC will be like 1 minus omega squared, and so on, right? So so these are roots of unity. I'm just gonna assume people know what that is for this class. So the expression we want is just gonna be all of this stuff. So AB times AC times AD times AE. That's just this, and this. Yeah. So what might we do with like this expression? Oh, so we don't have a 1 minus omega to the 5th, because then that would be 0. 1 is equal to omega to the 5th, so you don't want to multiply the expression by 0. So this is our answer. So yeah, how can I simplify this a little bit? Anyone have any thoughts? Adrita says 1 minus omega to the 4th is 1 minus omega. Yeah, that's true. The product of the magnitude is the magnitudes of the product. Yeah, that's the fact we're also going to use. Yeah. So yeah, that's good. So you can prove that with complex numbers, like A magnitude, B magnitude is AB magnitude. So the product of the magnitudes, it's the same as multiplying the numbers first and then taking the magnitude. And that's kind of what we proved earlier too. So also by symmetry, these two, like omega to the 4th is omega to the -1. And basically omega to the -1 and omega, they're like conjugates of each other, right? Because they both have magnitude 1 and they have the opposite arguments. So these are the same and these are the same. So we can sort of like remove the absolute values, because the this argument will cancel with this argument. So I'll just say arguments cancel, and similarly these two, they have opposite angles or arguments, so those will cancel. So it'll give a real number when you pair up like that. So then this is just like well, yeah. So, are there any questions up to here, I guess? I'm just gonna check what y'all are saying in chat. Yeah. So, one way is you can use the fact that 1 minus omega is the same as this, but we'll just leave it like this. We'll just leave it like the way I wrote it up here. So, this looks like the roots of some polynomial, right? So it looks like we're plugging in 1 into something. So let's say we have a polynomial p of x, right? So I'll just say it's x minus omega squared, and so on. So we want to find p of 1, right? But, what happens if I multiply this out, right? So what, this is like saying which polynomial has the 5 primitive roots of fifth roots of unity as the roots. So, we want a polynomial with these 4 complex numbers as the roots. Well, so I know that if I took, if I added in the point A as a root, so if I had like q of x is 1 minus x times p of x, then, hang on, I meant to say, so if you have this, then this is just x to the 5th minus 1, right? Because, so let me finish writing this. This is just, because basically, by definition, the roots of this are the 5th roots of unity, and these are the 5 5th roots of unity. So then p of x is just q of x, over like x minus 1. So that means, p of x is just x to the 5th, and then we, kind of divide out that root. So, this is just, by the geometric series formula, it's just this. So that's p of x. So the reason we define p of x is because this is just p of 1, right? So this is p of 1. So yeah, so now we just need to find p of 1. So on the one hand, p of 1 is just 1, it's just 5. On the other hand, this factors into, the product of x minus omega to the k. K equals 1 to 4. And that was the same as this expression with the magnitudes, because these arguments canceled out and the magnitudes multiply. So yeah. So the answer is just 5. And this generalizes to any number. It's not just true for pentagons. It'll work for like octagons or nonagons or whatever. Like, yeah. So in general, for an n-gon, if the circumradius is 1, the product of like P1 to P2, P1 to Pn minus, or let's just say Pn, is going to be n. If it's a regular polygon inscribed in a circle of circumradius 1. So the same argument works. Like, let's just check it works for a square, right? So this is 1, this is 1. So P1, P2, P3, P4. So the product of these 3 lengths is, this is root 2 times root 2 times 2. So that's 4. And 4 is the number of sides, so that works. If you want to check it for a hexagon, you can. Like a regular hexagon inscribed in the circle of radius 1. So these 5 lengths, they should have product 6, is the thing I just proved. So this is like 1 times root 3 times 2 times root 3 times 1, and that's 6. So yeah, in general, this product will be like n. And that's assuming it's a regular polygon with circumradius 1. And you prove it with this like polynomial trick about complex roots and stuff. Okay, so that wasn't the main thing I wanted to talk about, but it's kind of an okay problem, so we should have, it's good to talk about it. So let's look at this problem. Let me just bring up my. Okay. So can I remove this chat? Maybe not. Oh well. Okay, so you have, an isosceles right triangle, right angle at B. Let's put it in blue. Equilateral triangle, DEF, and D is the midpoint of BC. F is on AB, E is on AC, and AB is 4. So what's the area of, so we need the side length of the equilateral triangle. Yeah. And yeah, so any thoughts on this? Well, so, I guess, since today it's like geometry, I'll just teach the methods. So basically, we're going to use the main theorem that we proved earlier, which is when you multiply two complex numbers, you add their angles and you multiply their magnitudes. So let's just put it, let's see. I guess we can make D. Since it's an equilateral triangle, that makes us think of 60-degree rotations. So let's put D at the origin. So it's 0 plus 0i. This is 2 plus, this is negative 2. This is negative 2 plus 4i. So we'll put it in the complex plane. So I want to find like the coordinates of E and F in the complex plane. So let's just say the affix here is E, that can be F. So, well, what can we write down about this, right? So I know, let's say like, so E is basically F rotated by negative 60 degrees, right? So F is AI. So I'm not sure what you mean by that, but because I put D as the origin. So the reason I put, you can make B the origin, but let's just make D the origin. So, here is, the vector E. If I rotate it by 60 degrees, it becomes F, right? Because, E and F, they're equidistant from D, and that's 60 degrees. So basically, we can say F is going to be E times cis of 60 degrees. So that's, like E 1 plus I root 3 over 2. So, that's because we're multiplying by, something with argument 60 and magnitude 1. So, that's one fact we can write down. Another thing is that, F, so F, like the real part of it is like negative 2. So real part is negative 2. E, it lies on the plane, like, so E lies on like x plus y equals 2, like if you put it, in the coordinate plane, right? Because here's the x-axis, here's the y-axis, and, this line is x plus y equals 2. So, yeah, so, the reason I set D to be the origin is so that I can use this without like shifting vectors around. So, this is using the main theorem, and now we can just compute and solve for E and F. So yeah, is there any question on the setup here? So we have like these 3 pieces of information. Yeah, sorry, my chat is all the way over there, so I have to look over here to see if someone's saying something. But you can also just say things out loud if you really want to. Okay, so then, I guess we should compute. Like, let's say E has, I guess we might as well just use as few coordinates as possible, right? So E, it lies on this. So we'll just say it has like coordinates M and 2 minus M, because that's what it means to lie on this line. This was a right isosceles triangle, so this is 45, and it's a 1, 1, root 2 triangle for ABC. So then F is going to be, so we do 1/2 plus, so cis of 60 times M plus 2 minus Mi, and that will be the coordinates of F. So that's F. So it's 60 times E. So if we multiply it out, you'll get some stuff. So plus M minus 2 over 2, and then plus I times, so 2 minus M over 2, plus like root 3 M over 2. So that's the coordinates of F. And then we want to choose M so that like F has real part -2, because it's on this vertical line right here. So then this is the real part. So 1/2 M plus M over 2 minus 1 equals -2. So what is this? This is M equals what? -1. I feel like this is more simple than. I feel a little uncomfortable if this is right or not, but maybe it's right. Maybe I messed something up. So that means the x coordinate of E was -1, and this is like 3. So E is -1 plus 3i. Something about this doesn't seem right. I think that's not right. Yeah, you have to multiply that by root 3 over 2. Oh yeah, did I mess something up? Yeah, you're right. So let's see, 1/2 times that, and then yeah, so there should be an I root. So yeah, 1/2 M, and then this times this. So this is I squared, which I put in the -1, and then root 3 over 2. And I put in the 2, but I forgot the root 3. Okay, yeah, thanks to the catch, Eli. I think that's right now. So okay, great. Yeah. So this will be 1/2 M plus M root 3 over 2 minus 1 over 1 root 3. And then that equals -2 is the real part of F. Okay, yeah, I remember doing this a while back, and the numbers were definitely not this as nice as earlier. So yeah, but basically from here, it's just computation. So maybe I'm not going to worry about the computation so much. Like you can compute the answer from here, because once you know M, you know the coordinates of E. And once you know the coordinates of E, it's whatever M is, you plug it in. You find the distance to the origin, and that's the length of the equilateral triangle. And then you just find the area of the equilateral triangle, DEF. So I'm not going to waste time by computing it. So let's just look at the next problem. But anytime you have an equilateral triangle, you might consider like using complex numbers to do a 60-degree rotation if you want to bash it in the complex plane. And if you try to do the previous math prize problem with just coordinates, it's kind of ugly. So I'm pretty sure complex numbers are like the cleanest way to compute the answer. I couldn't figure out how to set it up with coordinates super easily. So I think, using complex numbers is actually really nice in that problem. Okay, so the thing is the answer 22 root 3 minus 36. Yeah, I think that looks really familiar. So yeah, I'm gonna say yes. It's from 2009, I think. So you can just look it up on the Math Prize for Girls website. 2009, maybe number 13 or 14. Yeah, that's for the problem we just did. So if we look at this Amy problem, let's see. So the main thing I wanted to talk about here, we don't have to compute the answer. But basically, this condition, it looks a little arbitrary. So basically, this is just saying it's cyclic. So you have 3 complex numbers, Z1, Z2, and Z3. And then Z is a 4th complex number with the property such that so I'll just write it out. So if you put these on a circle, this is equivalent to Z1, Z2, Z3, Z4 being concyclic. Well, it's not Z4, it's just Z being cyclic. So, let's say you draw a circle. Let's see. So there's 2 cases, I guess. So let's say Z is here. Maybe this is Z2, Z3, and Z1. So if you look at this thing, right? If you look at this, Z3 minus Z1, that's this vector, from there to there, with that length and that magnitude. I mean, that argument. Z2 minus Z1 is this vector. So when you divide the 2 complex numbers, formed by those 2 vectors, you'll just get this angle times some constant, right? Those 4 numbers are a parallelogram. No, they're not necessarily a parallelogram. It's cyclic, not parallelogram. Usually those will not coincide. I mean, maybe I drew it like that, but it's not necessarily true, and it's probably false. So, so basically, this will be some magnitude times. So I put cis negative theta, right? Because we're doing this number. If Z1 is the origin, we're doing this number divided by this number, so I'll have negative the magnitude of theta in my picture. And then if this is Z without a subscript, then you have Z, Z replaces Z1 kind of in the, this expression. So if you have Z minus Z2, that'll be this vector. So Z minus Z2. And then Z minus Z3 is like this. So I probably, So I think I'm just gonna rewrite this part as we'll just multiply the top by -1 and the bottom by -1. So just to make it cleaner to look at. So let's just cross that out and write it like this. So then we can draw the arrows the other way, because I want to interpret it more geometrically. So z2 minus z is going to be this thing, and z3 minus z is going to be that thing. So when we divide, this will have some angle, this will have some angle, and basically, if this is like alpha for this angle between the two vectors z2 minus z and z3 minus z, then let's see. So yeah, it'll be like, this will be like some magnitude times cis of negative alpha. So then, when we multiply these two, we'll just multiply the whatever the magnitudes are, it doesn't matter, and then we'll add the angles, right? So the resulting thing, when we multiply this red fraction times the thing I boxed in blue, it'll just have like, magnitude negative theta plus negative. So this will be the argument. And then it's like, it doesn't matter what the magnitude is. So it says this is a real number, right? So the only way this can be real is if the argument is a multiple of pi, right? So a multiple of 180 degrees. So I'll just say k times pi radians. So yeah, and you can kind of see from the picture that it has to be 0 or 180 basically, like depending on the configuration. So it's also possible that if z was right here, it's like 0, because then you'll have like, you'll have this diagram. Well, let's just finish with the first diagram. So here we'll just say it's equal to pi or negative pi or something, right? A multiple of pi, an integer multiple of pi, because it's real. So yeah, so that means you just have to find, for this problem, if you want to compute the answer, you just find the circumcircle of the points with these 3 points, as the vertices of a triangle. And then you want to make the imaginary part of z as big as possible. So you just pick the top point on the circle. So, you can like use whatever, like the equation of the perpendicular bisectors to find the circumcircle center, and then just go straight up to find, find the equation of the circle and find the highest point on the circle. And it just becomes a geometry problem. So yeah, so this fact is really common in Olympiad geometry. It's just saying like the 4 points are concyclic. And you prove it by looking at the angles that are formed by like the ratios of those like complex numbers. So yeah, any questions on this? So, it might take a while to digest, to check all the angle stuff. There's one more case, which is like if z, so let's just put z1 roughly the same place, z2 and z3 roughly the same place. So, we still have like, this is unchanged. But if you put z somewhere else on the circle, like if I put z right here, then you have like this and this. So now, you have, negative theta in the blue fraction. But if we look at the new fraction, z2 minus z, z2 minus z over z3 minus z, that'll be this angle, right? That'll be alpha. So then this is saying like, cis of negative theta times cis of positive alpha is a multiple of pi radians. So this time, because z and z1 are on the same side of the circle from z2 and z3, this will be 0 times pi. So you just get like, when you multiply these, you just add the angles and you'll get that like alpha minus theta equals 0 radians, 0 pi radians. So alpha equals theta, and that's a sufficient condition for like this to be concyclic. You can prove that if the two angles here are equal, then the 4 points are concyclic. So then it just becomes the same geometry problem. So you get every point on the circle except maybe like, except z cannot be like equal to z1 or z2 or z3. Like if z equals z3, then you get a division by 0 problem. But if you just, it can probably be like any other point on the circle. So, the locus of all z that satisfy the problem is basically a circle except z3. So locus of z is circumcircle of z1, z2, z3, except z3, except the point z3. So yeah, it's kind of like a locus problem where you have to find the set of all points that satisfy some arbitrary condition. And this arbitrary condition is really well known to be like a concyclic condition for 4 points. Okay. So, I said I do like 45 minutes of teaching, and then do you guys have any questions that you want to ask me? I said after I do this, I would just take any questions. It doesn't have to be related to this. It can be like, how do I self-study math better or something like that. And you can whisper the questions to me, and if you want, I can just not say who's asking the question. So in this thing, I think you can whisper by like, if you go to the username, if you go to participants, and then there's like a ... and then there's like send private message if you click that. Yeah. So I'm not going to go over particular math questions unless I know there's no like general questions about studying math. But we can go over like, because I have some other questions planned. I just want to make sure like I'm allowing office hours for random questions. And